Every second you play a game, your screen is rebuilt 60, 100, sometimes hundreds of times. And every one of those frames is assembled out of millions of tiny triangles, each one placed in 3 dimensions, lit, shaded, wrapped in texture, and then flattened down onto your 2-dimensional screen. The amount of math behind a single frame is staggering. Your CPU, for all its brilliance, would choke on it. And yet it happens, smoothly and effortlessly, thanks to a completely different kind of chip sitting right beside it. Ask most people what's inside a computer, and they'll say a processor and some memory. The CPU and the RAM. And that's true, but it quietly leaves out one of the most important pieces of silicon in the entire machine. Because for anything visual, and more for artificial intelligence, the real workhorse is the GPU, the graphics processing unit. And here's the key. It is not simply a faster CPU. It is built on a completely different philosophy. Here is that difference, and it's everything. A CPU has a handful of extremely powerful cores. Maybe 4, or 8, or 16. Each one is a genius, fast, flexible, and brilliant at long, winding sequences of decisions where each step depends on the one before it. A GPU throws that whole idea out. Instead of a few geniuses, it crams in thousands of much simpler, much weaker cores. Not a few brilliant minds. A vast, disciplined army. And an army is hopeless at a task that must be done one careful step at a time. But picture asking a CPU to color 2 million pixels. With its small handful of cores, it has to grind through them in little batches, a few at a time, millions of batches deep. Even blazingly fast, the sheer count buries it. A GPU colors thousands of those pixels in the very same instant. For this kind of work, 1,000 average workers utterly crush 8 superstars. So the GPU superpower is this. Take a job that splits into thousands of identical, independent pieces and do every piece at the very same time. The exact same operation, applied to an enormous pile of data, all in a single beat. Computer scientists call it data parallelism. One instruction, thousands of pieces of data, marching in perfect lockstep. It is useless for tangled, sequential logic, and unbeatable for vast, repetitive math. And it turns out that drawing graphics is almost the perfect job for an army like this. Think about it. Every single pixel on your screen can be colored completely independently of its neighbors. Every corner of every triangle can be repositioned without caring about the others. There is no long chain of dependencies, just the same few operations repeated across millions of points. Graphics is, in the jargon, embarrassingly parallel. It practically begs for a GPU. But before that army can do anything, it needs its materials right beside it. A GPU has its own private memory, called VRAM, kept separate from your computer's main system RAM. And for graphics memory, the headline number isn't really its size. It's its bandwidth, how much data it can move every second. A modern graphics card shovels data between its cores and its memory at hundreds, even thousands of gigabytes per second, far faster than ordinary system memory could ever dream of. Feeding the army quickly is everything. So, the very first step in drawing anything is to hand the GPU its raw materials. Your program uploads the scene, the lists of triangle corners, the textures, the little programs, across a connection from main memory into that fast VRAM. And from that moment on, the GPU takes over. What happens next is a beautiful fixed assembly line called the graphics pipeline. Let's follow a single triangle all the way down it. It all begins with vertices, the corner points of triangles. Nearly everything you see in a 3D game, every character, every wall, every blade of grass, is ultimately just a mesh of triangles. And a triangle is nothing more than 3 points in space. The GPU receives a long list of these points, each one carrying its position in the 3-dimensional world, and usually some extra notes, like which direction it faces and where it sits on a texture. The first real stage is the vertex shader, and it runs once for every single vertex, thousands of them, all at the same time. Its job is to take each point's position out in the 3D world and work out exactly where it lands on your flat screen. That takes a cascade of matrix multiplications, swinging the point around to the camera's point of view, then projecting 3 dimensions down into 2. Thousands of vertices, the identical transformation, computed in one parallel sweep. Once every corner knows its place on screen, the GPU snaps them back together into triangles and does a little housekeeping. Triangles that fell entirely off-screen are thrown away. Triangles hanging over the edge are clipped neatly to fit. And triangles facing away from you, the hidden backsides of solid objects, are cold and discarded, so not a scrap of effort is wasted drawing what you could never see. Only the triangles that actually matter move on. Now comes the step that genuinely feels like magic: rasterization. Up to this point, our triangle is still just 3 points and 3 crisped edges. Pure geometry. But your screen is a grid of pixels. Rasterization is the process of working out exactly which pixels fall inside that triangle and lighting them up as candidates. A clean mathematical shape is shattered into a spray of little pixel-sized pieces. This is the precise moment that geometry becomes a picture. Each of those candidate pixels is called a fragment, and a single full-screen scene can spawn many millions of them. And here, once again, the army goes to work, because every fragment can be handled completely independently of every other one. They never need to talk to each other. They simply need to be colored, all of them, at the very same time. That coloring happens in the fragment shader, and it is where a scene truly comes alive. For every fragment in parallel, the GPU runs a small program that decides its final color. It samples textures to paint on surface detail. It calculates how light strikes that exact point, how shiny it is, what shadows fall across it. Millions upon millions of these tiny color computations all happening at once are what turn flat geometry into something that genuinely looks real. One of the fragment shader's most important tricks is texturing, wrapping a flat image, a photo of brick or wood or skin, around bare 3D geometry. Remember those extra notes each vertex carried? Some of them are texture coordinates, telling the GPU which part of the image maps to which part of the surface. The shader looks up exactly the right spec of that image for every fragment. It's how a handful of plain gray triangles can suddenly become weathered stone, or rusted steel, or a human face. But there's a problem lurking. In a 3D scene, things overlap. A near wall hides a far one. So, when two fragments land on the very same pixel, how does the GPU know which one should win? It keeps a second hidden image called the depth buffer, or Z buffer, that records for every pixel how far away the closest thing drawn so far is. When a new fragment arrives, the GPU asks one question: are you nearer than what's already there? If yes, you're drawn. If not, you're thrown out. Pixel by pixel, the nearest always wins. The fragments that survive are blended together, any transparency mixed in and written into the final image, called the frame buffer. And the very instant that image is complete, it is handed off to your monitor and painted across the screen. Then, perhaps a 60th of a second later, the entire pipeline fires again, from scratch, for the next frame. Vertices: rasterize, shade, depth test, display. Over and over and over for as long as the game runs. Now here's the clever part you might have missed. Those shaders, the vertex shader and the fragment shader, are not fixed hardware. They are little programs that developers actually write, and the GPU runs your program across thousands of cores at the same time. Want water that ripples? Fire that flickers? Skin that softly glows? You write a tiny shader, and the GPU executes it on every relevant point in parallel. That programmability is exactly what makes modern graphics so endlessly, dazzlingly expressive. Stack it all together and the numbers become almost impossible to picture. A single modern game frame can involve millions of triangles and tens of millions of fragments, each one needing its own little burst of math, and the whole thing must finish in well under 1/100th of a second to keep the motion smooth. A high-end GPU performs tens of trillions of these calculations every single second. It is, quite simply, one of the most parallel machines humanity has ever built. And here is the plot twist that reshaped the entire technology industry. People realized that the GPU superpower, doing the same simple math on gigantic piles of numbers in parallel, is exactly, precisely what training a neural network demands. Because a neural network, at its very heart, is just enormous stacks of multiplications and additions across huge grids of numbers. The very chips built to draw triangles turned out to be the perfect engines for artificial intelligence. So researchers began using graphics cards for work that had nothing whatsoever to do with graphics, a practice called general-purpose GPU computing. Toolkits were built to let any program borrow that whole army of cores. And today, the largest AI models on Earth are trained inside warehouses packed with thousands of GPUs, humming away in parallel, doing the very same kind of math they were born to do for video games, just aimed at a brand new problem. So that is the real division of labor inside your machine. The CPU is a latency machine, built to finish any one complicated task as fast as it possibly can, a master of logic, branching, and orchestration. The GPU is a throughput machine, not especially quick at any single thing, but able to do a truly staggering number of simple things all in the same instant. One is a sports car, flat out fast for a single trip. The other is a 1,000-lane highway. So the next time a game paints an entire sprawling world in a single eye blink, or an AI conjures an image out of pure noise, remember what is actually happening underneath. An army of thousands of tiny cores, each one doing humble, repetitive arithmetic, all marching together in perfect lockstep. It was never really about raw speed. It was about doing a million small things at exactly the same time. That is the quiet genius of the GPU.